Hello and welcome to another Project 152, your weekly specialist exam prep. Now every week we go through questions from the QCAA. If you stick with us from now until the end of the exam, you'll have done every one of the 152 questions they've ever released. Now this week we are doing the week 26 solutions. Let's get started. So an interesting first question to kick off here. It's kind of a vibes-based question rather than doing a whole bunch of calculations. Now what do we have? We have a population distribution here, and we're taking samples of size 10, and these are our distributions of those sample means. So we're taking continuous samples of size 10. Now we should know that if we take a large enough sample size, quotation marks, if we take a large enough sample size, then as we move from the population distribution to the distribution of the sample means, we would expect it to look like a normal distribution. But we're not taking enormous sample sizes here. Now that doesn't mean that our distribution won't begin to look normal. There's no clearly defined, when the sample size is 29, it's not normal distribution. When it's 30, it is normal distribution. But these sample means, these distributions, look more and more like normal distributions the larger this sample size becomes. Which is why I'm very happy to disregard A here. And the reason I want to disregard A is because it looks nothing like a normal distribution, right? It still has exactly the same shape as my population distribution, despite having a sample size of 10. So we would expect it to be at least normal distribution-ish looking. Okay, so like I said, this is a vibes-based question. A is out. There is another reason that A is out. I'm going to talk about that now. Now I'm going to jump in, look at my formula sheet here, and I'm going to look at this standard deviation. Standard deviation is a measure of spread. Now, if we look at our population distribution, it's spread out from 0 to 20. Now, if we look at this, the standard deviation of our sample means is going to be equal to the measure of spread of our population divided by the square root of the sample size. In this case, divided by the square root of 10, which is about 3. So, if I divide this distribution by 3, it's going to shrink down to about, 7 from end to end. Which is why I'm very happy to disregard D here. Because look at the distribution of D. It's going from 0 all the way to 20. The distribution's too wide, given that we're calculating a sample mean. So I'm getting rid of A. I'm getting rid of D. That's another reason why I can get rid of A. You can see that's quite wide still. I expect that distribution to be much smaller. So I'm down to A, and I'm down to B, and I'm choosing between these options, so B and C. So which one of these am I going to choose? It feels like I might be able to disregard C because the spread feels too large. It's like from 4 to 16, so it's about 12. But I'm not happy with that as a reason. I'm going to use another reason for it. And the reason I'm going to use is the sample mean. So the mean, that is the average of this, is supposed to be equal to the average of whatever these two are. Now, because this one's pretty symmetrical, the mean and the median are about equal, and the mean of this is about 10. Now again, this is pretty symmetrical, and we can see that the mean of this is about 4. So the mean of this is supposed to equal the mean of this. Now, what's the mean of this? I can do like a little bit of a back of the envelope calculation on what the mean of this is. Lots of people in this 0 to 2 category, lots of people in this one, few people in this one, few people in this one. If I think of where the average would be here, the average is only going to be around here, around 4, 5, 6-ish, which is why this is going to be my answer. The average for this at 10 is way too large. The average of this distribution is definitely not 10, so I can get rid of this one. My final answer is going to be B. So this question, very, very vibes based. You're looking at it and you're coming up with, hey, how spread out should I expect this to be? Where are the averages in this compared to this? go from there. Don't forget to celebrate. And next question. All right, so this question, very, very fast in comparison to the last one. A confidence interval for a parameter is a range of values within which the, and then 4 options. Now, you're used to doing confidence intervals for the population mean, right? You take a sample and you find the mean of that sample, and then either side of that is your confidence interval. So the question is, a confidence interval for a parameter, in our case for the population mean, is a range of values within which the sample estimate of the parameter always lies. Yes, right? The sample estimate is the thing that you've done by taking the sample. You've estimated the population mean. The confidence interval will always be within our confidence interval. So A is the answer. What about B? Sample estimate of the parameter never lies? Well, obviously not the case. What about the parameter always lies? The parameter in this case is the population mean. And the population mean doesn't always lie within our confidence interval. If we've got a 95% confidence interval, the actual population mean will be outside of our confidence interval about 5% of the time. Parameter never lies. No, it will be inside of here 95% of the time. So my answer is A. Celebrate. So, nice little matrix of question here. Given A equals this, B equals this, and C equals this, determine X in this matrix equation. So before we get stuck worrying about the actual matrices, we can just manipulate this to make X the subject. Alright, so I've got XA minus XC equals B. I can use something called the left distributive law, bring X outside of these brackets, and I get A minus C equals B. Okay, and now we're doing something called post-multiplication. Now remember, A minus C is a single matrix. Imagine doing A minus C. You'll get a single 2 by 2 matrix. We can do the inverse of that. So I'm going to do X, A minus C times the inverse of A minus C. I've got to do it to both sides. So that's B times A minus C, the inverse of that. Now, this matrix times its inverse leaves me with the identity matrix right there. And this is still just B, A minus C, inverse. And of course, X times the identity matrix. We're left with X equals B, A minus C, negative 1. So, all of this work to now have a nice little matrix expression, B times the inverse of A minus C. That's what X is going to be equal to. And now it's just simply putting those matrices into this expression. All right, stepping through it slowly, X is equal to B. All right, so there's B. So let's make our little matrix here. It's 0, 2, 1, 3. Now we're going to swap colors here to make sure that we're being very obvious. Now we're going to do the inverse of, and then we put our first matrix inside it, which is A. 1, negative 2, 1, 2, minus, and then our next one is C, negative 1, negative 1, 0, 3. Okay, and there are our two matrices, A minus C. And finally, we're going to do the inverse of that. And then we just got to keep things in order and move slowly through this. So my first step here is just going to be subtracting these two matrices, one from the other. Now this is a tech-free question, so you've got to go tech-free. 1 minus minus 1, so 1 plus 1 is 2. Negative 2 minus minus 1, that's negative 2 plus 1, so that's negative 1. 1 minus 0 is 1, and 2 minus 3 is negative 1. That single matrix that I've created, we're finding the inverse of it. So now we're going to have to find the inverse of that matrix. Now it's one of those things you should probably know, but it is on your formula sheet. So here we go. The multiplicative inverse is equal to 1 over the determinant of A, D, negative B, negative C, A. What's the determinant? Don't worry, I've got you there as well. Alright, so there's the determinant AD minus BC. Alright, so let's do that up here. We just rewrite this one again. So we're doing the inverse of our pink one here. So 1 over A times D, so 2 times negative 1 is negative 2. And minus 1 times negative 1, which is negative 1, but we're doing minus negative 1. Right. So that's negative 2 plus 1, which is negative 1. So 1 over negative 1, I'll deal with that in a second. And then we have to do this swap. So this one moves to here, the negative 1 moves up here, and this one changes signs. So negative 1 becomes positive 1, and 1 becomes negative 1. All right, so from here, I have 0, 2, 1, 3. This is just negative 1. So if I take this matrix and multiply each element by negative 1, it just flips all the signs. 1, negative 1, 1, and negative 2. And now I just need to do some matrix multiplication. So we're going to have 4 elements here. It's going to be row 1 times column 1. So 0 times 1 is 0, plus 2 times 1 is 2. So my answer there is 2. And then for this element, it's going to be row 1, column 2. So 0 times negative 1, 0. 2 times negative 2, negative 4. And then we're going to get, for this element, it's row 2, column 1. 1 times 1 plus 3 times 1, that's 4. And finally, row 2 times column 2. 1 times negative 1 is negative 1. 3 times negative 2 is negative 6. Add them together, and I get negative 7. Job done. 5 relatively straightforward marks as long as you understand how to rearrange it using your left distributive law and you remember how to do this stuff. Tech free. Celebrate. So a nice little proof by induction question here. And the QCAA is being quite kind because they're saying part A, tell us the initial statement. Part B, do the inductive step. Part C, do the conclusion. Very cutesy, very demure. Let's do part A. So part A says we need to prove the initial statement. So let's see. N is true for all positive integers. So the first positive integer is 1. So let's prove true for n equals 1. And then we just split that into our left-hand side and our right-hand side. Now the left-hand side of this, very straightforward. We're looking at our first term here, and that's 1. Now what about our right-hand side? Now our right-hand side, you've got to be careful here. R is just some value. R to the n, now n is 1. R to the 1 minus 1 over R minus 1. Now, of course, R to the 1 is just R. So this is R minus 1 over R minus 1. And anything divided by itself is 1. So, therefore, true for n equals 1, because the left-hand side and the right-hand side are equal. That's part A done. Now, part B says we're going to do the inductive step. They've already done the assumption. They've already assumed that it's true for n equals k. So for the inductive step, we need to prove true for k plus 1. Okay, so let's rewrite this again, but with this k plus 1 idea embedded within it. So we have 1 plus r squared plus dot 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 plus r to the k minus 1, and then we've got to add one more term. And so the next term is going to be one more, so k plus 1 minus 1, which is just k, rk. Alright, and then on the right hand side, we're doing this k plus 1 idea. So it's r to the k plus 1 minus 1 over r minus 1, no k there. Now this is what we're required to prove. I like to put a little RTP here to say that this is required to prove. Haven't proven it yet, but this is what I want to prove. And now that I know that I want to prove that, I'm going to split this into a left-hand side and a right-hand side. Alright, so left-hand side, right-hand side, and then I'm going to use my left-hand side here, and this is always the case with partial sums, and we use our assumption in here somehow. Now notice this. In our assumption, it says that 1 plus r squared plus r blah 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 r to the k minus 1 equals r to the k minus 1 over r minus 1. So I can replace all of this with what that says it's equal to. R to the k minus 1 over, is it r minus 1? And then I've got this plus r to the k there. So now the question is, how do I make that look like that? Or I guess I could make that look like that. But one way or another, I need to make those look the same. Okay, well, that's one fraction. That's two fractions. So maybe what I should do is make it so that I can turn this into a single fraction. So the easiest way to do that is to make them both have the same denominator. So r to the k minus 1 over r minus 1 plus r to the k, and then multiply top and bottom by r minus 1. R minus 1, r minus 1. And now I'm going to do two jobs here. First of all, it's a single fraction now, r minus 1. I've got this r to the k minus 1 still in business, and then I can do r to the k times r. Let's think about that for a second. R to the k times r. That's the same as r to the k times r to the 1. And your index laws would tell you that we can add those powers together. So we get r to the k plus 1 when we multiply this by this. R to the k plus 1. And then we have r to the k times negative 1, which is negative r to the k. Getting very, very close because I can see an r to the k and a negative r to the k, so they're going to cancel each other out. Look up here, I've got an r to the k plus 1, I've got a negative 1, so I'll just write this r minus 1 on the bottom, and then this r to the k plus 1, and then finally this negative 1 here. Done. That r to the k, the negative r to the k, they cancel out. Left hand side is equal to the right hand side. Final step, because we've done part B now, we need an answer to part C, just the conclusion. This is the conclusion that the QCAA comes up with. The rule is proven for n equals k plus 1. By mathematical induction, the rule is true for n equals 1, 2, etc., etc., etc. That's it. Conclusion. Single mark for something that looks like that. Celebrate. So an interesting looking question here, because this is question 18, which means it's one of the most difficult questions on the exam, but it is just very straightforward. We've got a differential equation, and we're solving the differential equation. That is it. All right, let's write it down. All right, so there's our equation, and we can see it's x's and y's, dy dx. This is a separation of variables style question. So let's move all of the x's to one side and all of the y's to the other side. So tan y, that's going to move up here, tan y, dy, and we're going to integrate that. And on the other side, the dx is moving up to here, and we're left with x over x squared plus 1. And so now we've got two integrals, one on each side, and we've just got to solve both of these. Neither of them are particularly easy. So I don't know of a good way of integrating tan y, but I do know that tan y can be expressed as sine y over cos y. So I'm going to start there. All right, so I've got it written here. I'm going to solve it here, and then I'm going to move it back over to here. So now I've got tan y equals sine y over cos y, and this should feel like we can do some integration by substitution. The reason I'm thinking integration by substitution is because cos y and sine y derivatives of each other. So I'm going to let cos y equal u, and I know that the derivative of u with respect to y, so the derivative of cos y is negative sine y. And I can rearrange this now as du over negative sine y equals dy. And now that I've done this little piece of work, I can substitute a bunch of this stuff into my integral. So, integral sine y. Now, leave sine y where it was. Cos y is equal to u. And then what do I get? I get a du negative sine y to replace my dy here. Great, fantastic, because I've got this sine y and this sine y that cancels out. I've still got that negative there, be careful. So this is equal to the integral of negative 1 on u with respect to u. Integrating this, very, very straightforward. It's equal to negative ln u. Of course, with a little plus c on the end, but u is not u. U is cos y. Negative ln cos y plus c. Now, I really should put some absolute values in here. Done and done. All right, all of this work, the integral of tan y with respect to y is equal to negative ln cos y plus c. Now, I have put the negative ln cos y there. I might just leave off the plus c because I'm going to integrate this side as well. I'm going to end up with a plus c's there as well. So let's put that aside for a second. All right, let's get rid of all of this because we're going to do the same trick again with this one. All right, so if we see x over x squared plus 1, some of us will be able to jump straight to the answer, essentially, but I'm going to use the same trick. I'm going to use that substitution thing because what I notice is x squared and x, they're related to each other. X is basically the derivative of x squared plus 1. It's the same order that the derivative would be. So I'm going to let x squared plus 1 equal u. And that means that the derivative of u with respect to x is just equal to 2x. And then I can rearrange that and get dx du over 2x. All right, let's put a box around that. And we can now put that information into our integral. So we've got the integral of x over x squared plus 1 equals u. And then instead of dx, we're going to go du 2x. All right, we can see that x, they're going to cancel each other out. We've still got that 2 there. I might just bring it out the front. We've got, let's be a little more formal here, equals 1/2 integral 1 on u with respect to u. Okay, feeling like we're going to get to another natural log, half ln u, and then this plus c here. Of course, u isn't u. Oh, don't forget your absolute values. Of course, u isn't u, it's ln x squared plus 1 plus c. All right, if you know a faster way to do this, like f dash of x over f of x, you can do it that way, but I wanted to show you this substitution method. All right, let's take this, put it here. Now, the next logical step here is to say, okay, well, I know all this now, but I don't know this c value. It says passes through the origin. That means when x equals 0, y equals 0, and I can sub x equals 0 and y equals 0 into this equation. All right, so putting 0 in for y and 0 in for x, what happens here? Got to do it stages. Cos 0 is equal to 1. All right, so now the question is, what is ln 1? Natural log of 1 is 0. So all of this, negative 0, 0. Done. Okay, what about this? Again, we've got natural log of 0 squared plus 1. So the natural log of 1, which is 0. 0 times 1/2 is 0. So we get 0 equals 0 plus c. So 0 equals c. Okay, so even if you'd forgotten to put that c in there, we'd end up with the correct answer because the c disappears. The value of c is 0. Okay, so we're here. We've got this equation right now because there's no more plus c. The plus c is gone. Let's talk about these absolute values for a second. Look at the bounds. It says where x is greater than or equal to 0. So this will always be greater than or equal to 0 as well, right? Because if x is 1 or 2 or 3 or 4, that's always going to be positive. So the absolute values there are just a bit superfluous. We've just got x squared plus 1. We can do a similar trick over here. Because we're told that y is between negative pi on 2 and 0 in the fourth quadrant. And cos in the fourth quadrant is always positive. So there's no need to put these absolute values in here. We've just got negative ln cos y equals half ln x squared plus 1. That's an equation, but it says we need it in the form x equals f of I. So we've got to start simplifying this, making it x equals something. So what do I notice? ln's on both sides, but I've got like a negative 1 out the front here, and I've got a 1/2 here. If I just had it ln something and ln something, I could move forward from there. And I think I can do it because I can raise this to the power of negative 1 and raise this to the power of 1/2. All right, so that's one of our log laws. We can just take those as powers. So what does this mean? It means ln 1 on cos y, raising something to the power of negative 1. And what does this mean? It means ln square root x squared plus 1. So if I've got ln something is equal to ln something, then that means that the something is equal to the something. We can get rid of the logs. Now it does seem a little bit silly to be writing 1 over cos y over and over and over again, because we've got reciprocal trig functions, so we should use one of those. So 1 over cos y is equal to sec y. So let's just replace that with sec y. So we want to make x the subject. We're getting very close. Next thing we need to do is get rid of this square root. So we've got sec squared y, because we're squaring both sides, is equal to x squared plus 1. I can subtract 1. X squared equals sec squared y minus 1. And at this stage, alarm bells should be going off because you know your formula sheet very, very well. Pythagorean identities. Now, we've got a sec squared minus 1. Look at our second one here. Tan squared a plus 1 equals sec squared. So if I move the negative 1 to the other side, we can say that sec squared y minus 1 is equal to tan squared y. So now I've got tan squared y equals x squared. Okay, what do I need to do? I want x is equal to something. X is equal to the square root of tan squared y. Now, of course, if you're square rooting something, plus or minus. Now, the square root of something squared is just equal to itself, right? So plus or minus tan y x. X is equal to plus or minus tan y. Now the question does have one last trick to throw at us, and you're going to have to think hard about this. Is it plus tan y equals x, or is it negative tan y equals x? It's here that the clues are. All right, so we know, first of all, that y is in the fourth quadrant. Okay, y is in the fourth quadrant. Boom. We also know that when an angle is in the fourth quadrant, tan of that angle is going to be a negative value, right? Tan is negative in the fourth quadrant. Let me move out of the way. Tan is negative in the fourth quadrant. So, if we go positive tan y, we're going to get a negative x value. But, it says here that x is always greater than or equal to 0. So, in order for us to get a positive x value out of this, we're going to need to have negative tan y is equal to x. Now that I've written that, let's take one more look at it. Tan y in the fourth quadrant is negative, but because I've said negative tan y, that's going to be positive, which is what we expect because x needs to be greater than or equal to 0. There is our final answer. X equals negative tan y. Celebrate! Alright, let's go. The gradient function of f of x is defined as this. Determine f of x. So we've got to integrate g of x to get f of x, and the integration is going to be fun. Alright, so integrating this, I can only think of one thing, and that is a function multiplied by a function. We are thinking integration by parts. There is my formula. Now, the way I like to think about integration by parts is this acronym, detail, and this tells me which of these I'm going to choose to be dy dx. So is there an exponential function here? Yes, there is. There's e to the x. So that's going to be my dy dx, or what I call my v dash. Okay, so my v dash is going to be e to the x, and my v is going to be the integral of that, which is e to the x. Now that means that the other one is going to be my u. So inverse sine ex, and I wonder what u dash is. Feels like I need to do a little bit of work for that one. Now I do have some help on my formula sheet here, because the derivative of inverse sine is equal to this thing here. Now I don't have inverse sine x, I have e to the x, so I guess I'm going to let e to the x equal w. So if I let e to the x equal w, I can find the derivative of u with respect to x by finding the derivative of this, which I can find using this formula, 1 over the square root. Now an a value, there's just w divided by 1, square root of 1 squared, which is 1, minus x squared, which is w squared. We'll fix that in a minute. But this is a chain rule question, because I also need to multiply by the derivative of e to the x, which is of course e to the x. Now bringing all of this together, we have e to the x up the top, square root 1 minus, now w isn't w is e to the x, but we are going to square it as well, e to the x squared, and that's going to be equal to e to the 2x. So that becomes e to the 2x. Happy days, I can take that, and that is going to be my u dash. Now, unfortunately, we barely started because we haven't even started doing our integration by parts over here. So, our integration by parts formula says it's going to be equal to uv, so this times this. All right, that's u times v, and then we're subtracting the integral of v times du dx. So v is e to the x, so e to the x, and then multiplied by all of this, e to the x over root 1 minus e to the 2x. Now e to the x times e to the x, e to the x times e to the x, that's e to the 2x. So we can simplify this a little bit and just make it e to the 2x, a single fraction. All right, now it's not really still smooth sailing because this integral here looks like it's going to require some work as well. Now what do I notice here? I see this e to the 2x up the top, and I see this 1 minus e to the 2x on the bottom, and e to the 2x, e to the 2x, derivatives of each other. So I think I can put a substitution in here of like u equals 1 minus e to the 2x. So let's focus our energy on this piece right here. So if I let this piece, 1 minus e to the 2x equal u, du dx is going to be equal to the derivative of that, which is negative 2e to the 2x, and I can rearrange that a little bit to make du over negative 2e to the 2x equals dx. And it's this stuff here that I can now substitute into here, and hopefully I can get a nice little integral out of it. All right, so I've done the substitution here, e to the 2x. I've replaced the 1 minus e to the 2x with u, and I've replaced the dx with du minus 2e to the 2x. All right, so replace, done. What we can see is this e to the 2x and this e to the 2x cancel each other out, and we end up with the integral. We've still got this negative 1/2, so let's put that out the front. Negative 1/2, so that's positive 1/2 now out the front. 1 over the square root of u. Let's just write it as u to the 1/2 with respect to u. And now we're integrating this. Don't forget, we've still got all of that other stuff as well. Now this integral here, it's like a maths method style integral. U to the 1/2 on the bottom is the same as u to a negative 1/2 on the top. And so when I integrate that, we'll focus on this piece first. We're increasing the power by 1, so u to the negative 1/2 becomes u to the 1/2. So let's put that there. And then we're dividing by the new power. So dividing by a half, that's the same as multiplying by 2. Great. Now that means we've integrated this, but remember it was going to get multiplied by a half as well. So 2u to the half multiplied by a half makes u to the half. Now, of course, u is not u, but we'll deal with that in a second. For now, let's put the rest of our stuff there. Now, let's not forget we integrated here, so we've got a plus c on the end. And then finally, e to the x inverse sine e to the x. U is not u. U is 1 minus e to the 2x. And raising that to the power of a half, we get a square root there. I've got to close my bracket there. And a plus c on the end. Okay. I think I'm done. That's a whole integral now. The question does say the function f of x passes through the origin. So f of x equals 0 when x equals 0, which means we can solve this for c. All right, so solving this, I've put x equals 0, y equals 0 here. Now, e to the 0 is 1. Inverse sine of e to the 0. Now, again, e to the 0 is 1. So, inverse sine of 1. In other words, where is sine equal to 1? The answer is pi on 2. So, 1 times pi on 2 plus the square root of 1 minus e to the 0. 1 minus 1. The square root of 0 is 0. So, that's a big 0 there. Plus c. So that means that c is equal to negative 1 times pi on 2, which is negative pi on 2. This question is officially over. We know what c is. That's all we had to do. Let's write down our final answer. F of x equals all of that minus c, which is pi on 2. All right, just grunt work here, just endless grunt work. I wouldn't say it's my favorite question, but it's a question. Celebrate. So that's another week in the can. Week 26 done. Next week, week 27. I think we've got about 4 weeks left in us. Week 30 will be the end of it. I'll catch you in the next one.